In this video, we're going to look at an example of using the Biot Savart Law to determine a magnetic field. In this case, I have an infinite, or really long would be the actual way to look at that, but we're going to consider this to be an infinitely long straight wire carrying a steady current I. And I'm curious about the magnetic field a distance A away, that didn't turn out very well, a distance A away from the wire. So I'm going to have to use the Biot Savart Law for this. I guess I don't have to, but I'm going to. And we're going to have to integrate along this wire from negative infinity to infinity to see how each little bitty segment of this wire contributes. Our strategy is always to break up our source into infinitesimal or differential elements and then to see how they contribute. And so there's going to be a little section. Let's say, let me get a different color. Let's say there's going to be a little section of the current right here. That's going to be our IDL. I'll write that over here. IDL. Make sure you can see this. That is my little bitty segment of the current. And that is going to cause a portion of the magnetic field here at point A. So let's continue the geometry. Get a different color. This is going to be the distance, of course, R. That's the distance between the differential current element in my observation point. And of course, there's going to be directed along that line some R hat. Let me make this R hat and I'll put R over here just because I wrote that over here. There's going to be some sort of R hat here. And then along the direction of R. And what I didn't put in was that my IDL should also be a vector, right? That is my IDL. It's this differential current element. Because I'm using the Biot Savart Law and I need to use a cross product, I'm going to have to explicitly tell you that this is a vector. Of course, once I do that, you can see that the angle between DL and R is this angle. We'll say that that is theta, if you can see that. And we'll look at that geometry in just a second. But this is my setup. I've got a long straight wire. I'm looking at a distance A away from it. I'm going to have to form IDL, R hat, and then I've got my geometry. Now, before I just run through it, let's look at a few things that will make this easier down the line. Notice that R is going to be, if I call this the y-axis, I'm going to be integrating along the y-axis, of course. Then this distance R is going to be wherever I am, y squared plus a squared square root. I'm always a distance A away on this side of the triangle. Over here, I'm going to let that range, and so I've got a y squared plus a squared square root. I can do more than that, though, because remember, DL is always a placeholder. DL just is something that I'm going to fill in with my actual direction later, and so in this case, I'm going to be integrating along the y-axis, so why don't I just remind myself now that I'm going to be able to write DL as some dy y hat. That is taking care of the direction and the magnitude. Here's a differential element, so that's dy, and the direction is going to be in the y hat. And I need to be really more specific with my current. I put this here to remind you that it's going to infinity, but we're going to say that my current is moving up. So this arrow just tells you it's going to infinity. I'm actually saying the current is moving up in this direction. Of course, that's going to make a difference to the direction of our field, so let's be explicit with that. So when I integrate, I'm going to integrate along with the current from negative infinity to positive infinity. This is going to negative, this is going to positive. So I'm going to have to integrate way down here to way up there. So I've taken care of this geometry, I've taken care of this geometry. Let's take care of the theta. Just to remind you of a little bit of geometry, let me move over here to the side. So if this is theta, which it certainly is, then this, of course, is equal to pi minus theta, right? Pi would be our 180 degrees. And let me remind you of the trig here. Sine of theta is equal to the sine of pi minus theta. So that will make actually seeing how to handle the geometry here a little bit better if I just remember that what I'm looking at is not just this, it's not just, it's not just this angle, but this angle, if I'm talking about the sine of the sine of these two angles is equivalent, and this one's really easy to figure out. I can see that now. I can even go ahead and write it down. The sine of theta will be the same as the sine of pi minus theta. And just from the geometry here, that is going to be opposite over hypotenuse A over R. All right, what am I going to do with all this? Well, I'm going to attempt to determine the magnetic field of this wire using the Biot Savart Law. So let me write down the Biot Savart Law. It tells me that the differential contribution to the magnetic field due to my differential current element is equal to mu naught over 4 pi integral, and I've already figured out that I'm going to have to go from minus infinity to infinity of I dl cross r hat over r squared. That is my Biot Savart Law. Now that I've written this down in the general form, let's do some replacing from what I already have here. Before we do that, let's pull out anything that's constant. I is constant, that's why I write di as idl in the first place, and so that I can pull out the constant. So let me do that. It's equal to mu naught I over 4 pi integral negative infinity infinity dl cross r hat over r squared. All right, fair enough. Now, let's see if I can make this a little bit easier on myself by going ahead and handling the cross product. So let me just take an aside. I'm not going to write over here because I don't have much room in the margin, but let me just go down here. So we're gonna come back to this step, but let me take some do some side work here. dl I've already characterized as dy y hat cross r hat. Now, my strategy here is going to be to write this cross product as its magnitude from the definition of a cross product times its direction from the right-hand rule. What in the world do you mean by that? Well, remember, I will go over the margin for this. By definition, A cross B is equal to magnitude of A times the magnitude of B times the sine of the angle between them times the unit vector orthogonal to both of these, determined usually by the right-hand rule. All right, this is just the definition of the cross product. Let me remind you of that. Now, what that means is that I can rewrite this cross product in terms of the definition. So the magnitude of dy y hat is just dy, right? Unit vectors have a magnitude of 1. That's why we use them. Y hat has a magnitude of 1. R hat has a magnitude of 1. So I can rewrite the magnitude of this as just dy. And then times the magnitude of this, but that's just times 1. So why don't I just skip that step and I just get a dy. But what I do get out of it is the sine of the angle between them. Well, what is the angle between them? Here's dy and here's r hat. The sine of that angle, which is theta, I've already determined is the same as the sine of the interior angle here. So I can write that now as A over R. So dy sine of theta, which I will write as dy times A over R, but what is R? But y squared plus A squared. Square root. Okay, so I've taken care of the cross product, I've taken care of the geometry. Now, in case that was fast, let me just assure you that the first time I saw this problem, it didn't click anywhere nearly this fast, and so I would encourage you to go back and rewatch what we just did, pause and think, pause and work out. Get a pencil and a paper and try to work this out yourself step by step, right? Pause and see if you can work out the next step and let the video play. Because that's the advantage of videos. You can stop and watch. This is not something that I would just expect you to go, oh, of course, that's exactly how it works. Go back and see if you can figure it out from the beginning. Start out with this and run through the geometry, and then form your Biot Savart Law, and then plug in the things that you've already figured out are constant or make the substitutions, and see if you can get to this point. Now, once we're at that point, I can now go back to this step and put in this stuff that I know back into my Biot Savart Law integrand. So, back to the normal stuff. Let me go ahead and integrate the left-hand side. I should have written that up here. If I'm integrating the right-hand side, I need to integrate the left-hand side. Let me just go ahead and do that. This is b, and that's going to equal to all my constants, mu naught I over 4 pi, mu naught I over 4 pi. And then I'm going to have an integral from negative infinity to infinity. And I'm going to have this 1 over r squared, which I will write as this term squared, just y squared plus a squared. So I'm going to get here y squared plus a squared. And then I have dy a over y squared plus a squared square root. This is the cross product. So this is 1 over r squared from here. This is the cross product dl cross r hat. I can write that up here. I'm going to get a times dy. Notice now I've got a y squared plus a squared, and I've got a y squared plus a squared square root. So I think at this point we can probably skip the step of writing that out and just do this. And that is an integral with a form which we have seen before. Let me go to a new sheet and work that out. Well, I can get a new sheet. There we go. So let me rewrite that integral. B is equal to mu naught over 4 pi. There was an I here. Let me go ahead, if it's all right with y'all, and pull out this constant, right? We just got an A, that's a constant. Mu naught I A over 4 pi. Integral negative infinity to infinity of dy over y squared plus a squared to the 3/2 power. One more thing I can do here to make it easier on myself, to recognize that this is an even function, and it's evaluated over symmetric limits. Mathematically, that lets me know that I can just change my lower limit to 0 and multiply the whole thing by 2. So let me do that. 2 times this is going to get me a 1/2, not a 1/4. So this is going to have to be equal to mu naught IA over 2 pi. Integral now from 0 to infinity dy over y squared plus a squared to the 3/2 power. That was a mathematical consideration. If you want the physical consideration, it's this. I is constant. All the contributions from up here are going to have to equal the contributions from down here because I is not changing. And just from the physical symmetry, everything down here is going to contribute a certain amount. Everything up here will contribute the exact same amount. So make it easier on yourself. Do half of the integral, multiply it by 2. That's the physical consideration. Mathematically, it's an even function evaluated over symmetric limits. It gets me this. Okay, well, let's take care of this integral. If I look this up on a table, I'm going to get mu naught, or evaluate it explicitly if you so desire, over 2 pi times, this evaluates as y over a squared times y squared plus a squared to the 1/2 power. Make sure I'm not out of frame. And that's going to be evaluated at my limits, 0 to infinity. Of course, evaluating at infinity means I'm going to have to look at the behavior as y gets really large. Infinity is not a number to plug in, so the idea of a limit comes in here, of course. Lower limit's easy though. If I'm plugging in 0 for y, I'm going to get 0 in the numerator. This becomes 0 at the lower limit. I don't have to worry about that. What happens when I plug it in what happens when I plug in really large numbers here? The idea that you should be thinking of is that a is a constant, never changes. So as y gets bigger and bigger and bigger and bigger, then y starts to dominate. And a squared doesn't contribute a whole lot. Y squared plus a squared, if y is getting really large, basically becomes y squared. Think about it. If y is a billion and a is 2, then you've got a billion squared plus 4. Isn't that about a billion squared? And as y gets bigger and bigger, that effect gets more and more pronounced. And so if I take the limit here as y approaches infinity, I get y over the square root of y squared, which is just y. So I get a 1 from everything, from the y and everything in parentheses. So 1 times, what am I left with out here? 1 over a squared. So at the upper limit, this just becomes 1 over a squared. So I get mu naught IA over 2 pi a squared. I can get rid of that and get rid of that. And what I come up with is mu naught I over 2 pi a. Now, if you were paying attention, you go, wait, hold up. You forgot the direction. And if you're thinking that, you're absolutely right. Let's go back and pick that up. Nothing wrong with what we just did. But this step here, I rewrote this as the magnitude. What I left off was the direction. I've got to be really clever about this. Y hat cross R hat. Notice, no matter how I swing that, no matter where I am on this axis, a y hat is going to be pointing upwards. So y hat cross r hat, point my fingers in the direction of the first one, which looks like this. Let me move this over. Curl them into the direction of the second one, right? Keep hitting my camera. Y hat cross r hat gives me a vector into the page. Notice we're going to have cylindrical symmetry coming about here. So r hat is not constant. Absolutely it's not. Y hat is. R hat is not constant. But the cross product of y hat cross r hat will be a constant vector into the page. That's how it works in cylindrical symmetry. The cylindrical component, the z hat usually is what it's called, is constant. R hat is not constant. So the cross product here between the y direction and the r hat, y hat and r hat is going to be z hat, which is a constant. So what I can do now is when I evaluated this in terms of its magnitude, I just tack on a z hat. Right? I guess I should point out that many of you might be using j hat for y and k hat for z. That's totally fine. I much prefer the z hats, but k hats work for me as well. Which means, of course, because this is constant, it can come outside of the integral. So I can write k hat there. I can write k hat here, k hat here, k hat here, k hat here, and k hat here. So I would say I actually did forget to do this when I was going through the problem. My apologies for that. But I would say that even if I was working this problem again, and I'd already seen that that was going to be constant, I would actually probably just neglect it until the end. Because what as soon as I figure out that it's constant and I can take it out of the integral, I know that I can work with the magnitude and just tack on the directional dependence later. Either way works, right? But what you get here is a field at a distance a away from the wire, pointing into the page, of mu naught I over 2 pi a. If you compare that with on your formula sheet for the magnetic field due to a long straight wire, what you get is mu naught I over 2 pi r, where r is the distance from the wire to the source. This is usually written in vector form like this. to remind you that if you're looking at this wire edge on, so here's the wire coming towards you, you have a magnetic field that looks like this in the theta hat direction, where theta hat's the unit vector attached at every point. For this particular case, now notice what we're doing. We just picked off one point. We picked off this point. So if I look at my original drawing, and I shift my perspective to where I'm looking down on the wire, I'm just looking at one point over here. That would be this perspective looking at this point. So at this point, I have a unit vector coming up, which is what I found here, because I determined that at the point A away from in that particular location, I got this vector into the page. The plane of the page, if I flipped this up, this is the plane of the page. And so I get the vector going into the page exactly like what I got. So we've got to think a little bit to match up this specific result to our general result. But it actually does work. So I'd encourage you to go through that problem a few times from scratch. Make sure you understand how to solve it. Specifically, make sure you understand what we did here with the cross product to get it into a form easily evaluable.